All right, good morning. My name is Debendra Das Sharma, and I work for Intel. I'm a PCI-SIG board member. I'm going to talk about PCI Express, what's coming up in general for the technology and more specifically for the storage. Here's a brief agenda. We'll talk about how PCI Express has evolved, how it delivers power-efficient performance, significant number of RAS enhancements that we have done over the years, I/O virtualization, different form factors, compliance program by the PCI-SIG, and the conclusions. PCI-SIG is a fairly huge body with 750 member companies worldwide, and has developed the I/O technologies for more than 3 decades, right? And we'll talk about that. So fairly healthy ecosystem that exists with the PCI-SIG and with the PCI Express technology that we drive. Back in 1992, this is what the PCI-X based system used to look like. It was a bus-based system. You had multiple PCI devices sitting on the bus. You had a CPU connected to a host bridge, memory used to be there, and this was more of a PC-centric technology. Graphics was not on PCI bus, it was an AGP bus, and then you got either PCI devices hooked directly to the host bridge, or you had bridges followed by bridges, and then you had a bunch of PCI devices hanging off the bridge. So we started in 1992 with PCI. There were about 5 to 6 generations of evolution in that technology. You started off with around 32 bits, 33 megahertz, went to 64 bits, 33 megahertz, 64 bits, 66 megahertz, every single time effectively doubling the bandwidth on the bus, and went for 5 generation 6 if you count the QDR data rate that happened with PCI. And at some point, bus-based systems ran out of bandwidth. You cannot deliver enough bandwidth when multiple devices coexist on a bus. So around 2004, we moved from a bus-based interconnect to a links-based interconnect, which is the PCI Express. It's a full duplex differential signaling because it's much more pin efficient. You can deliver a lot of bandwidth with a lot less pins. All of these backwards compatibility that existed with the bus-based system, when we moved to the links-based interconnect, you cannot make things in a hardware backwards compatible manner. Silicon-based compatibility or even form factor-based compatibility, we had to break those. But what we did was we maintained the software-based backwards compatibility. You can still take a PCI driver and it will run on the PCI Express-based system. And we also maintained the architectural producer-consumer ordering model for data consistency. Those are the critical pieces that carried along. We evolved on top of that, but the fundamental basics of it was continued forward, so you could completely interoperate even through this transition. And during that, the transition basically looked like you got CPU, you got your root complex. Notice that graphics becomes PCI Express. And then these are direct PCI Express links in which you have networking, storage, or you could go through switches and build your hierarchy of PCI Express, or you could even put a PCI bridge in order to manage that transition, because not everybody would have moved from PCI bus-based devices to PCI Express-based links. So that's how the transition was managed. It was fairly successful from that perspective, especially with the bridges and especially with software-based backwards compatibility. It was a fairly smooth transition. Around 2004, we had the first generation of PCI Express based systems out and available in the marketplace. And then evolution has continued. From there, we have moved into an SoC-based methodology where everything gets integrated into the CPU, and we'll see a picture of that. But effectively, everything goes into a CPU complex here. You got PCI Express links coming out directly from the CPU. And currently, we are in the 5th generation of the technology. We double the bandwidth every single generation, right? So 2004 through now, we are on the verge of delivering the 5th generation of the technology. So 32x in terms of the bandwidth per pin, right? Every single generation we double the bandwidth. And during this journey, the entire compute landscape has seen a lot of changes. right? We have moved from PC-based systems to mostly handheld devices and a bunch of devices that are out there, right? The things and devices connected to data centers and the edge and everything. So the compute landscape has changed significantly, and all throughout this, PCI Express has remained as the ubiquitous I/O technology that is driving this revolution. In the context of storage, what has happened is that because of all of these things and devices, billions of them that are out there, there is an explosion in the data. And with data, you have to have three things that needs to happen. You have to store more, you have to move more, and you have to process more. And that is what is triggering this, what we call virtuous cycle of growth. So from a storage perspective, there is a data explosion that is driving SSD innovations and adoption. And you will see that, if you look into PCI Express versus other types of interconnects that connect to the storage, we are on the upswing, right? Whether it is number of units or whether it is the number of petabytes, and the CAGRs are already there. But fundamentally what's happening is, when you have this volume of data, when you have to process so much, what is the interconnect that can deliver you the lower latency, the higher bandwidth, right? And bandwidth that is scalable bandwidth, not just from a speeds and feeds point of view. In PCI Express, you can move single lane, 2 lanes, 4 lanes, 8 lanes, all the way to 16 lanes and deliver a lot of the bandwidth in a low latency manner coming from the CPU. The natural choice is PCI Express, and with NVM Express, that move happened very rapidly, and that is what is moving a lot of this move into the PCI Express based links. When that happens, when fundamentally storage is no longer the bottleneck, there is a lot of pressure on the networking side because you need to move the data faster. So there is more of a revolution going on there. The transition from 10 to 40 to 100 to 200 is happening at a much more faster pace than what probably anybody would have projected 4 or 5 years back. And when that happens, the other thing that is happening is you have to process the data. So you got a lot of AI, neural networks, all of that kind of things that are coming in, and you see a bunch of accelerators coming up. Right? All of that is driving a lot of bandwidth demand on the I/O, and which is the virtuous cycle that I referred to. So whether it is in the context of storage or any other application, we'll take a look into this in more detail. There is a pictorial version of it, but PCI Express 3.0 came out in 2010, products were out in 2011, and I will show a picture of that. 4.0, 2017, 5.0, we are expecting 0.9 end of this year for the spec, and a final version of the spec sometime in Q1 of 2019. So this picture speaks to that particular evolution that I was referring to. Around 2004, we came out with Gen 1. At that time, you had CPUs connected through the front side bus. And this is, in the server context, normally we refer to the highest volume is 2-socket server. So everything is normalized here with respect to, up until this point, right, is with respect to a 2-socket based system. So CPUs are connected through front side bus. You got your hub here that is connecting to memory, which is an ASIC, and then you got a bunch of PCI Express lanes coming out. At that time, there were about 28 lanes coming out. So if you do it on a per CPU socket basis, you get 14 lanes per CPU socket. Notice that I/O has moved to differential signaling in this time frame, whereas the coherency link is still on a bus-based system, right? So I/O has preceded in terms of where CPU to CPU connectivity had been. And this is not just, this is across the board, right? Across different vendors, if you look into it in that time frame. From 2.5 gigatransfers per second, PCIe Gen 2 products came out in 2007 in the market. And by this time frame, notice that memory has moved to the CPU, right? In order to get more memory bandwidth. Demand is going up, so you need to deliver not just more number of cores, but more amount of memory bandwidth. You got to feed the beast. And then these are the coherency-based links, and you still had an I/O hub kind of a concept, which was basically which you take the coherent link and transfer it into PCI Express. Notice the lane count, it has gone up from 14 lanes per socket to either 18 or 36 lanes per socket, depending on a rich I/O kind of a topology, in which you will deliver 36 times to 72 lanes of PCI Express. Those that don't need as much, you will deliver 36 lanes of PCI Express. Doubling the bandwidth, and also more than doubling the number of lanes, depending on your usage model. PCI Express Gen 3 based products come out in 2011, and you got CPUs connected through coherency links, and you got memory. And just like memory had moved to the CPU, PCI Express moves to the CPU. Huge move from an interconnect technology point of view. In order to get into the CPU, you have to be the ubiquitous I/O of choice. If there are 5 or 6 contenders, you're not going to put them on the CPU. You will put some kind of a translator chip and then have I/O coming out of it, right? So by then, it's already well established that on a platform, you're not going to spend the real estate, the power, and all of that through a different component. With Moore's law, as you're getting more and more die area on the CPU, you move things into the CPU, right? That's where CPU I/O gets integrated into the CPU. Number of lane count increases yet again. Starting, it was 40 lanes. And today, if you look into, a lot of people are offering more than 100 lanes of PCI Express coming out of the CPU socket. Right? Huge number of lanes coming out of the CPU socket. And again, if you look into the usages, networking tends to be, you will put one networking device, typically a per slot bandwidth consumer, which is the per slot bandwidth that is being shown here. Storage will be lots of storage devices, lots of SSDs on the system. So it's a fan-out consumer. More number of lanes is what it wants to consume, and also it's an aggregate I/O bandwidth consumer. Right? You are going to aggregate your bandwidth across multiple devices, and accelerators are in both the categories. Right? They can consume, each of them can consume as much bandwidth as you can deliver, and people are putting multiple accelerators in the system. Right? Combination of all of these three are moving both the vectors forward. Right? Number of lanes per socket and bandwidth per pin, or which is the frequency, speeds and feeds, right? Both of them are getting pushed up. Gen 4 time frame, you have 16 gigatransfers per second. That's when the spec comes out. And then Gen 5 is 32 gigatransfers per second. As I said, we are expecting it in 0.9 is pretty much when things are more or less stable. We are expecting that this year, by the end of this year. And Q1 2019 is when the 1.0 will come out. So we are doubling the data rate every single generation. Now you'll notice that 5 to 8 is not quite the doubling of the data rate, but what happened was we changed the fundamental encoding mechanism. We moved from an 8-bit 10B encoding to 128B 130B encoding. So if you take the encoding efficiency, it's 1.25 gain multiplied by 1.6 in the data rate, and you got a 2x improvement in the bandwidth per pin. The reason we did that is The reason we did that is that we wanted to still maintain the 20-inch 2 connector connection in the server without requiring any retimer kind of a device, or without requiring expensive material, or without requiring extra power, right? Any of these trade-offs you can make and run the link at 10 gigatransfers per second. But in the interest of making the technology not become a niche, we decided to take the hit on the logic side, put an extra encoder on the logic, which is, again, with Moore's law, that's not a big deal, but keep the channel reach the same. But Gen 3 to Gen 4, you either have to have better materials, and there is enough time in here for us to go and make the changes in the entire industry, because what used to be lower loss material, expensive material, are now becoming more and more mainstream on the board. So a lot of people can route on their servers by making the channels a little shorter without requiring retimers. And those that need the extra length have got retimer-based devices to extend the channel reach. In addition to the speeds and feeds, you will see that we are introducing new things in terms of the protocol. Around the Gen 2 time frame, we introduced I/O virtualization. So this is where you had multiple virtual machines running on the server, and in order to give customers or users the experience as if each VM owns its own device. So we virtualize the devices. So that way you can do a direct association between a VM and a virtual function, or a VM or a virtual device. Effectively, a device can present itself as multiple virtual devices, and you can associate them. And PCI Express as a specification enabled that by making all of those I/O virtualization extensions on the base specification itself. So those are part of that, and this is when the products started reflecting I/O virtualization in the root complex, right, as well as on the device side. When Gen 3 came along, you will notice that there are atomic ops, caching hints, lower latency, and fundamentally what's happening there is, in this time frame, accelerators are becoming popular, and you want to be able to have a way to offer an accelerator to atomic operations, not just to the host memory, but also amongst themselves through the CPU host. So PCI Express base specification got modified to introduce the notion of atomic operations. So you could atomically modify things, right? Different atomic operations were introduced. We introduced the notion of caching hints and lower latency, especially with I/O moving into the CPU. What can happen is you can now take advantage of the caching hierarchy inside the CPU. That way, effectively your descriptors and things like that you are reusing often can reside in the caching hierarchy. You don't have to go to the system memory in order, or even worse, you don't have to go through the coherent link to the system memory on the other side to access those. So things that you are going to access more frequently, you could take advantage of it through hints on the link, and the processing element there would try to keep it in its caching hierarchy, because you give the hint that you're going to have locality of reference as far as those addresses are concerned. And effectively, what that has enabled us to do is that has made the transition for example, networking fairly smooth, because we could store all the descriptors locally in the last level cache, and then the cores can access them without having to go to the memory. And that has enabled us to deliver 10 gigabit networking as well as 40 and all of that very smoothly, right? People that were way back when people were looking into TCP offload on Ethernet, the thinking there was there is going to be so much of processing involved, there is going to be so much of going back and forth to the system memory involved that it's better to do all of that processing outside. With all of these changes, we haven't seen that becoming the bottleneck. We have been able to deliver the line rate on PCI Express. Improved power management becomes an interesting concept in this time frame, because what has happened is during this compute evolution, handhelds have become very popular. And with PCI Express being a PC-based technology, we always had low power states. But our low power states were in the milliwatts range when you were. And if you have your system connected to a power supply, milliwatts is a fairly good low power state to be in. But once you are on your battery charged cell phone or whatever, right, milliwatts doesn't quite cut it, right? You need to be in the microwatts range, and that's where MIPI was doing a pretty good job. And at some point, we had even toyed with the notion of doing PCI Express protocol on MIPI 5. MPCIe was the concept that got introduced. However, that did not become very popular, because PCI Express, we went ahead and fixed the power saving state and introduced a very aggressive L1 substate notion that took our power consumption down in the idle system to microwatts range. So with all of these changes, right, you will see that we are always not just trying to double the data rate, but looking into the type of applications that are coming up, and we are making the right set of changes in the I/O technology to be able to match with those needs. So these are the things that are coming up, and then in addition to power enhancements, we have form factor and usage models. We'll talk about that. So fundamentally, we double the bandwidth every 3 to 4 years, and we make all the changes that we need to get the ecosystem going. PCI Express is a layered architecture, and that helps us make these transitions go through, right? So you'll say that the software, we try to preserve it. There are enhancements, but we try to preserve that. Transaction is a split transaction packet-based protocol, very modern concept introduced since the PCI Express Gen 1 days. Credit-based flow control, virtual channels to guarantee quality of service. Data link layer is responsible for reliable data transport services through CRC, retry, ACNAC, all of those things. So very high reliability-based links. And if you have done a failure in time analysis, you will see that this link is pretty much nothing gets through. Your fit is going to be significantly lower than 1. Let's put it in that way. Orders of magnitude lower than 1, right? Logical, phi, and electrical are there for physical information exchange, interface initialization, and maintenance. So because these are very specific functionality, whenever we do the data rate change, we just change this part. The rest of them remain the same. Whenever we make a protocol enhancements, we just make the changes here. The rest of them can remain the same. So you can make the changes in different parts without having to move everything at the same time. And then the mechanical is the specific one, which is, it's a market segment based form factor, because you don't really expect your form factors to be the same. Your form factor in a smartphone is very different than a form factor in a 2U chassis, for example, right? Very different form factor. So it's different types of form factors which PCI Express allows. But all of them work with the same silicon. You can take the silicon that came out in PCI Express Gen 1, single lane, and it's guaranteed to interoperate with a PCI Express Gen 5 device, which is 16 lanes. Of course, it will operate at the least common denominator, which is it will work as Gen 1 and by 1, but you've got interoperability across the board. And that's a guarantee by the way the specification has been done. PCI-SIG recently had a liaison with SD Association, and we are very excited about it. It has got a huge volume in the IoT and handheld segment, and SD is looking to start using PCI 3.0 to deliver higher data rate, and as you see that, and that's called SD Express, and it's going to take advantage of our compliance program, which we will talk about. It's a big volume, right? So we have an MOU, and we are doing this jointly. It'll run on PCI Express technology. PCI Express it delivers the power efficient performance, and from a scalability point of view, you got variable widths. You got by 1, you got by 2, by 4, by 8. By 12 is not popular, by 16, and technically there is a by 12 and technically there is a by 32, but those don't exist from a real market point of view, right? So you can just ignore the by 12 there. So width-wise you can scale, right? Single lane, 2 lanes, 4 lanes, 8 lanes, 16 lanes. Frequency-wise, we have got 5 generations like we talked about. And low power, as we were talking about earlier, we have a very rich set of link and device states. On the link side, we got different link substates, and I was talking about L1 substates, how that reduce the idle power consumption to microwatts. From a device power states, we have got a set of rich device power states, so that way not only is the link idle, but also you can put the device into a lower power state. And there are platform level optimization hooks, like dynamically you can allocate power. When you want to give more power to one device and less to the other device, you could do that dynamically in the platform. There is optimized buffer flush fill kind of mechanisms. The basic idea there is you want all of your I/O as well as processing to happen within a certain window, and then have the rest of the platform be at rest or in the idle state. So that way, this is trying to coordinate when multiple devices are being active. So that way, the platform can save more power. It doesn't help you if you have got 10 devices in the system, and at any given point of time, somebody is using the link, and the rest 9 of them are in a low power state. So this is trying to coordinate that activity. And this goes along with that. Every device reports how much of latency it can tolerate. So that way the platform can orchestrate the power savings going through the entire platform. We have very low active power. So idle power is in the, like I said, in the microwatts, standby power. Active power is in the 5 picojoule per bit. It's the best in the industry. Absolutely the best amongst any competing standard that can exist, right? And this is what you get with 700 plus companies, with an I/O that becomes ubiquitous. People will innovate, and when you got more and more people innovating, you are going to get the best numbers, and that helps, right? That's a good feedback loop that's going on. And the vibrant ecosystem with IP providers, so that way you can go and buy world-class IP from different vendors, and a lot of the IHVs tend to just focus on what they do the best, right? PCI Express, because it has got all of these ecosystem support, you can get IPs, you can get validation infrastructure, both pre-silicon and post-silicon. So SIG has got a good compliance program, so that part of it is taken care of. That way it helps people focus on the other things where they can add the value. PCI Express offers a rich set of RAS features: reliability, availability, and serviceability. All the transactions are protected by 32-bit CRC. Practically nothing passes through that. Right? With link level retry, and it can even cover dropped packets. So it has been that way since Gen 1 days. There is hierarchical timeout support, and by that what we mean is there are different levels of timeout in different parts of the hierarchy. So not all of them will be timing out at the same time, and you don't want multiple places where timeouts are happening, then you don't know what happened where, right? It's hierarchical in its nature, right? The one at the lowest level of the hierarchy will time out first, and the next level will time out. There is a bigger timer there, and it's all timer-based mechanism. A very well-defined algorithm for different error scenarios. We are very careful about not having things like what we call error pollution and all of those kind of things, which means that if there is an error, there is only one type of error that will get reported. Okay, because if there are multiple errors that happen for the same thing, then you just don't know what happened when, right? And not only that, you will also report exactly what happened. If it is a transaction type of an error, you've got the header that caused the error to be logged. So very elaborate set of advanced error reporting mechanism with logging and all of that information. Everything from the physical layer to the link layer to the transaction layer has its own error reporting mechanism. Whenever there is a lane error, a lane fails more often, you can go for degraded link width, right? Because we support all of those widths in a mandatory manner. If you have a by 16 link and one lane is failing often, you will go down to a by 8. If you got something again failing, you can go down to a by 4, to a by 2, to a by 1. So you got all of those support, and then support for hot plug, right? You can do either planned hot plug or you can do surprise hot plug, and the spec supports both. With the storage devices moving to PCI Express, we introduced the notion of downstream port containment and enhanced downstream port containment. And the basic idea there is, if you have a root complex and you got a PCIe hierarchy, and this can be each of them can be directly hooked to the root complex or go through a switches. The error or failure in one of the SSDs, you don't want them to bring down the other SSDs, and hence the notion of the downstream port containment. So what happens is that in these kind of usage model, asynchronous removal of the SSD is fairly common. So what happens to the transactions that are outstanding to that SSD, right? If I have reads, for example, that are outstanding to an SSD and they start timing out, then in my root port, then what happens is that if we didn't have all of these, I have no idea who it was targeting to, so I'm going to bring down the entire hierarchy, so my storage would become inaccessible. So this basically provided the enhancements, and it mandates that you're supposed to keep track of things on a per device kind of a basis, right, at a very high level. That's the idea here. So it defines that mechanism, and it tries to prevent the potential spread of corrupting the data while trying to keep the link backup. I/O virtualization. So this is the other aspect, which is we all know that we need virtualization to reduce system cost and power to improve the efficiency of the infrastructure and make sure that our infrastructure gets used more often. You don't want to have idle infrastructure sitting in your data center or even in your desktop or laptop or whatever, right? And or handheld for that matter. Single root I/O virtualization happened in 2007, and this allowed multiple VMs, right? Each of them is like a independent OS to coexist in the same system. All of them gets orchestrated through a I/O MMU, and you are taking a device. This is the PCIe device. This is a cartoon diagram of that. There is a physical function with multiple virtual functions, and this one gets assigned to that VM, that assigns to that VM, that assigns. Effectively, you are time slicing a device. Or if it is storage, you could start think of it in terms of you are allocating different units of storage to the VMs, right? So time or space slicing the device, and all of them get orchestrated through the virtual machine monitor, which controls the config accesses, but the rest of the DMA accesses happen directly between these. And what PCI Express provides is this notion of, it created this notion of physical function and virtual function, and it created the notion of the I/O MMU. If you want to make cast the I/O MMU locally, it allowed that. So it allowed for the notion of what is host physical address, guest physical address, and you can provide that and also ask for the translations from the root port, locally cache it, and if the root port wanted to purge a particular TLB entry, you would get a part of that command, and then you would respond, right? It also provided things like so that's the address translation services that it provided. It also provided with what is known as access control services. So that way, if you have a switch, imagine you have a switch hierarchy and a bunch of devices underneath that. You don't want the devices to be talking directly to each other, especially if they're allotted to different VMs. If the translation happens in the root complex, effectively what happens is everything goes back up and then comes down. That way you get the real physical translation happening in the root complex, and then you're taking it back down. So it defined all of those kind of the do's and the don'ts and codified in the base specification as to how things are supposed to work once you define that you are capable of doing ATS, which is the address translation service, or ACS, which is the access control service. Also, we introduced the notion of page request interface, and recently we introduced the notion of what we call PASID, process address space ID, to support direct assignment of I/O to the user space. So that way, you don't have to go through an indirect mechanism or go through the driver to access the I/O device. You could directly have the user space be exposed to the I/O. And that way, I/O can directly talk in the user space. So all of those mechanisms have been built into the spec. And these are more recent than the 2007 over there. So over time, these kind of things are moving on to take advantage or to enable the emerging usages that we see in the broader ecosystem. Switching gears now to the form factors. We have a range of form factors, right? So you got the low power NVMe, which is M.2 and U.2 kind of form factor. And these are mostly for your client kind of devices. You got the server performance and NVMe, both as an add-in card form factor as well as your U.2. You also have the high profile, the server performance NVMe with low profile but taller form factors, right? By 8 add-in card. And the power goes from low to high naturally, and so is the amount of bandwidth that you get as well as the capacity that you get, and the different EDSFF family of form factors that exist, and people are continuing to innovate in this area. So that way you are going to have petabytes and petabytes of storage with your servers. Right? So some of them are from the PCI-SIG, some of them are from other different other places that are coming through, but they all run on PCI Express technology. And this is where, again, the ecosystem will innovate based on the usage model, and we are happy to have that. Again, switching gears now, PCI-SIG has a very good compliance program. And SIG delivers the compliance program directly, right? So there are workshops that happen throughout the year, multiple workshops in multiple geos across the world. People come there with their devices, and the compliance program is fairly extensive. You test everything from electrically, whether your transmitters are having the right set of voltage and timing parameters, to check your receivers, whether you can tolerate stressed eye and all of that, to physical layer, do you link up properly under error conditions, to link layer, it will introduce errors, inject errors in the link and make sure that can you recover from that, to transaction layer, all the way to the software stack, right? It's a fairly extensive set of programs. So think of it as you got the specs. From the specs, the SIG takes that and does compliance and interoperability test specs. These are formal specs, right, that come out. And they happen, there is a little bit of lag, clearly. If your base spec cannot come out and the C&I test spec will be there like right away. 1 to 2 quarters later, they will come out. Then you got your test hardware and software that will come from that. And from there, you're going to run the entire compliance program, like I said, at each and every one of those layers. There is an extensive set of compliance test suite. We will test it across different speeds, feeds, all of that. And there is clearly a pass or a fail. If you fail, not the end of the world, you go back, fix it, come back, right? A lot of the people that I know just use the SIG compliance program to do the testing, because so if you're a small company, you don't want to have the infrastructure, you just take it to the compliance program, figure out where all you failed, try to debug it there, come back, turn the silicon and go back and do the testing again. So the basic goal is that we want a predictable path for design compliance. And again, just because you passed compliance doesn't necessarily mean that you will interrupt, but your chances of interoperability goes up significantly. Right? That's the whole idea here, right? And given that if you have an ecosystem of 750 companies, this is something that you need to do in order to make sure that people understand what it takes for something to interoperate. Otherwise, it's very hard to get different people innovating at the same time to interoperate, right? If you have an open slot, which is PCI Express, this is the thing that you need to do in order to make sure that people have a good customer experience, right? So in conclusion, from an I/O perspective, PCI Express is the ubiquitous I/O that goes across the entire compute continuum. Right? If you are on the CPU, pretty much you will have, of course, different CPUs targeted for the different segments, but they all have PCI Express coming out of them. It's a single standard. We do not have different standards for handheld, for desktop, for server. Same standard, same silicon. Different form factors, yes, but one standard, right, across the board. And that helps to focus our attention to deliver the best in class. Predominant direct interconnect, and again, scalable bandwidth, both in terms of frequency and width. Low power, definitely, that's ingrained into us, right? We need to be low power in order, not just for handheld, but also even for server, right? Server demands low power because if you consume a lot of power on the I/O, you have less power left on the compute, right? People want to have more power on the compute because that's where you are getting a lot of the compute done, right? So everybody is being squeezed to give more power back. So it's a common theme, right, across the board. High performance, of course, and predictive performance growth spanning 5 generations with a very robust and mature and compliance program, interoperability program, and the devices that are there everywhere, right? You can make a PCI device and connect anywhere and figure out whether it works or not, and so that helps in terms of the development. Not to mention the availability of wide range of IPs and infrastructure like testing infrastructure and all of that. All right, thank you very much.